Okay, example 3-2 is about channel contraction. So we have a horizontal and rectangular channel, which undergoes a gradual contraction. So the initial width of the channel is 2.8 meter. So here we have 2.8 meter, and then it reduced by 30%. So then B2 is going to be 0.7 times 2.8, so which is 1.96 meter. So 1.96 meter. So the upstream water depths and discharge are 1.65. So we have the side view, 1.65 meter. And then we have the discharge Q, which is 1.85 cubic meter per second. So assuming that the energy loss is negligible, so delta E is almost zero, calculate the water depths at the neck of contraction. So we want to know what is Y2. So what is the value of Y2 here? Then calculate the critical depth. So we know that in rectangular channels, the critical depth is only a function of discharge. So we can calculate critical depth. And the minimum channel width at the neck. So if we have the critical depth, what would be the minimum width? So we have critical depth, minimum width, and critical velocity. Okay, so first we want to calculate Y2. So using, for part A, using energy equation. So we have E1 is equal to E2 plus delta E. So energy loss is negligible, so almost zero. So we have E1 is equal to E2. And we know that E1 is equal to Y1 plus Q squared divided by 2G A squared, which is V1 Y1 squared, which is equal to Y2 plus Q squared divided by 2G B2 Y2 squared. So this is one equation, one unknown, because Y1, B1, B2, and Q are known. So I'm going to put the values here. So 1.65 plus 1.85 square divided by 2 times 9.81 times 2.8 times 1.65 square is equal to Y2 plus 1.85 square divided by 2 times 9.81 times 1.96 times Y2 square. Okay, so one equation, one unknown. You can either use Excel to solve it by try and error, or you can just solve the cubic equation with your calculator to get the value of Y2. So from that, you will get Y2 is equal to 1.64542 meters. So you'll see that due to channel contraction, the water level decreases by 8 millimeter. So 1.642 versus 1.65. So 8 millimeter water level drop due to channel contraction. So in part B, we want to calculate critical depth. So we know that YC is equal to a square root of Q squared divided by G. So you can either solve it in this method, which can be correct, or you could say that E1 is equal to E minimum, and then which is equal to, and then the left-hand side of this equation, you can calculate that, which gives you 1.658 meter. Okay, so which is 1.658, and it is equal to 2/3 of YC. So this is much easier than using the YC equal to Q squared divided by G, but you can do that as well. And both should give you the same answer. So here I have two. So here, then I have 1.658 times 3 times, so this is 3 divided by 2. So times 2 divided by 3 is equal to YC, which gives you 1.105 meter. So if you remember, in critical flow condition, Froude number is equal to 1. So Froude number in critical flow condition is equal to 1. Therefore, VC divided by square root of GYC is equal to 1. And then from that, we know that VC is equal to square root of GYC. Okay, so I have the critical depth, and from that I can calculate critical velocity, which is 9.81 times 1.105. This gives me the critical velocity of 3.29 meter per second. Okay. So in part C, now I can use continuity equation using continuity equation. So we have Q equal to YC VC B minimum. So you'd like to know that with the given energy budget at section 1, what would be the critical depths? And then once you have the critical depths, you can calculate critical velocity. And then that gives you the minimum width. So I have 1.85 is equal to 1.105 multiplied by 3.29 multiplied by B minimum. Okay, and then one equation, one unknown, you can find B minimum is equal to 0.508 meter. Okay, so this means that even if you reduce the channel width from 2.8 meter to slightly more than half a meter, you still can have the flow passing through the contraction without any change in the water level in section 1. Okay,